In mathematics, a cube root of a number x is a number as such that a3 equals x. All real numbers have exactly one real cube root in a pair of complex conjugate cube roots, and all non-zero complex numbers have three distinct complex cube roots. For example, the real cube root of 8, denoted as 2, because 23 equals 8. While the other cube roots of 8 are and the three cube roots of -27 the cube root operation is not associative or distributive with addition or subtraction. In some contexts, particularly when the number whose cube root is to be taken is a real number, one of the cube roots is referred to as the principal cube root. Denoted with the radical sign, the cube root operation is associative with exponentiation and distributive with multiplication and division if considering only real numbers, but not always if considering complex numbers. For example, the cube of any cube root of 8 is 8, but the three cube roots of a formal definition. The cube roots of a number x are the numbers y which satisfy the equation real numbers for any real number y. There is one real number x such that x3 equals y. The cube function is increasing, so does not give the same result for two different inputs, plus it covers all real numbers. In other words, it is a bijection, or 1-to-1. Then we can define an inverse function that is also 1-to-1. For real numbers, we can define a unique cube root of all real numbers. If this definition is used, the cube root of a negative number is a negative number. If x and y are allowed to be complex, then there are three solutions, and so x has three cube roots. A real number has one real cube root and two further cube roots which form a complex conjugate pair. This can lead to some interesting results. For instance, the cube roots of the number 1 are. The last two of these roots lead to a relationship between all roots of any real or complex number. If a number is one cube root of any real or complex number, the other two cube roots can be found by multiplying that number by one or the other of the two complex cube roots of one. Complex numbers. For complex numbers, the principal cube root is usually defined as the cube root that has the largest real part, or, equivalently, the cube root whose argument has the least absolute value. It is related to the principal value of the natural logarithm by the formula if we write x is where r is a non-negative real number and theta lies in the range, then the principal complex cube root is. This means that in polar coordinates, we are taking the cube root of the radius and dividing the polar angle by 3 in order to define a cube root. With this definition, the principal cube root of a negative number is a complex number, and for instance will not be. But rather this limitation can easily be avoided if we write the original complex number x in three equivalent forms, namely the principal complex cube roots of these three forms, or then respectively. In general, these three complex numbers are distinct, even though the three representations of x were the same. For example, may then be calculated to be -2, 1 plus I square root 3, or 1 minus I square root 3. In programs that are aware of the imaginary plane, the graph of the cube root of x on the real plane will not display any output for negative values of x. To also include negative roots, these programs must be explicitly instructed to only use real numbers. Impossibility of compass and straightedge construction. Cube roots arise in the problem of finding an angle whose measure is 1/3 that of a given angle, and in the problem of finding the edge of a cube whose volume is twice that of a cube with a given edge. In 1837, Pierre Untitled proved that neither of these can be done with the compass and straightedge construction. Numerical methods. Newton's method is an iterative method that can be used to calculate the cube root. For real floating point numbers, this method reduces to the following iterative algorithm to produce successively better approximations of the cube root of. The method is simply averaging three factors chosen such that at each iteration, Halley's method improves upon this with an algorithm that converges more quickly with each step, albeit consuming more multiplication operations. with either method. A poor initial approximation of can give very poor algorithm performance, and coming up with a good initial approximation is somewhat of a black art. Some implementations manipulate the exponent bits of the floating point number, i.e., they arrive at an initial approximation by dividing the exponent by 3. This has the disadvantage of requiring knowledge of the internal representation of the floating point number, and therefore a single implementation is not guaranteed to work across all computing platforms. Also useful is this generalized continued fraction, based on the nth root method. If x is a good first approximation to the cube root of z and y equals z minus x3, then the second equation combines each pair of fractions from the first into a single fraction, thus doubling the speed of convergence. The advantage is that x and y are only computed once. Appearance in solutions of third and fourth degree equations. Cubic equations, which are polynomial equations of the third degree, can always be solved for their 3 solutions in terms of cube roots and square roots. If 2 of the solutions are complex numbers, then all 3 solution expressions involve the real cube roots of 2 real numbers. While if all 3 solutions are real numbers, then each solution is expressed in terms of the complex cube roots of 2 complex numbers. Quartic equations can also be solved in terms of cube roots and square roots. History. The calculation of cube roots can be traced back to Babylonian mathematicians from as early as 1800 BCE. In the 4th century BCE, Plato posed the problem of doubling the cube, which required a compass and straightedge construction of the edge of a cube with twice the volume of a given cube. This required the construction, now known to be impossible, of the length the cube root of 2. A method for extracting cube roots appears in the 9 chapters on the mathematical art, a Chinese mathematical text compiled around the 2nd century BCE and commented on by Lu Hui in the 3rd century CE. The Greek mathematician Hero of Alexandria devised a method for calculating cube roots in the 1st century CE. His formula is again mentioned by Eutychios in a commentary on Archimedes. In 499 CE, Aryabhata, a mathematician-astronomer from the classical age of Indian mathematics and Indian astronomy, gave a method for finding the cube root of numbers having many digits in the Aryabhatiya.